Good morning. So today we're going to go through the Control Systems Lab 1. In this tutorial, we'll learn about Matlab, Simulink, and Simscape and how to use them to simulate a DC motor. The first step here is to download Matlab 2022A, and when it asks for all the different checkboxes, make sure to click the Simulink add-ins because we'll be using it for this tutorial. Once you have Matlab 2022A installed, the next thing you want to do is you want to type this line into your command window to ensure that the proper kernel is installed. This kernel was successfully installed. So here is the lab manual, which you can download from the links below, as well as the Matlab and Simulink and Simscape project files. So this initial information here is to do with explaining how the DC motor works and the resistors, inductors, and EMF voltages that are used to simulate that motor. So now let's get started with lab activity 1. So here, the first thing to do is to download the zip file from the links below and to open up the differential equation Simulink file. I have it here. Now this may take a bit of time to actually load, and so we'll just wait for that. You can see it telling you about the process as you go. Alright, so here we have the pre-built model, except there's some aspects missing, and through this tutorial you'll learn how to add these types of aspects back into the system. Let's make this slightly larger so we can see. So the first thing we want to do is add in this step. So there's multiple ways you can do this. You can use the library browser. You can see that it does take some time to open it up and then navigate through all of these different folders and blocks. So if you know what you want, you can simply double click and then type in the block that you're looking for. So here we get the step function, and by dragging it onto this line, it will automatically connect. Now let's add the next, the integrator. And you can see if sometimes it doesn't connect, drag it again until you do get that proper connection. If things are not properly connected, your model won't run. And so here, there's multiple integrators that we're adding in, one here, and one here. So let's add in those last two. So you can either do this double click again, or you can click on it and copy paste. So the first thing we want to do is we want to set up the step function to give a voltage signal to the motor and see what the output speed is going to be. The idea of this is that in real life we'll be controlling the voltage to emit a certain speed and position of the motor. So we click the step function to change the step time to 1 and the final value to 2. So if you double click, it'll open up these extra system parameters. So here we have step time as 1, final value of 2, and then click apply. So now we can see how this system works just by clicking the run button here. You can see it initializing and that here it completed the step. Once it's completed, you can use the scope here to see what the input voltage and the output speeds are. And so by double clicking it, you then get to see them here. So there's different things to note here. So you can use, so first of all, you have your motor rotation speed. You can see that as this input voltage stepped to that final value of 2, you can see that the position constantly increases, which makes sense. You add a voltage and the motor starts to spin, and then that rotation ends up being at a constant speed after this transient response happens, and then you see this constant speed at the steady state. Next, you can see that you can drag these traces, and as a result, you see the different time here, and the value along here. And you can even change this. So let's start with the motor input voltage, and let's say that we want to see the initial step voltage, which is 0. So at time before 1, we have value of 0. And then we can use the second trace here to see the voltage at that new time. So at time 2, voltage is 2. What's important to then look at is to look at this position and ultimately the speed to understand what the steady state speed value is. And so you can set this somewhat out here. You can change this to the motor rotation speed, and then you see the initial value is 0 and the final value is 45 or 4.5 e to the 1. Once you have this, you can copy this plot to clipboard. So file, copy to clipboard, click. And then for your reports, it looks much nicer when you then paste these inside, because they have a nice white nice white or clear background, unlike if you just do a screenshot of this and you get all these darker background and colors. Okay, great. So the next thing here is to see when we increase that voltage, what happens to the motor rotation speed and the angular position, to figure out really the transfer function of this model. For what kind of inputs, what kind of outputs do you receive? And so just as a reminder, here we had the motor rotation speed at 45 when we had that input step of 2. And so now let's double it. Let's bring it to 4 and see what the output is. So now we run the model. It will rebuild the data within the scope. And now you can see that we've, in a sense, doubled the output speed to 90 from 45. And so this shows that the voltage and the speed of your system are proportional. Let's see one more time. Let's double it one more time. So we're bringing this from 4 to 8, and we would expect something for the speed going from 90 to 180. And so it's just important you click run. By updating those model parameters, it doesn't automatically update the scope. You need to click the run button. And here you go. You can see that now the value at 2 is more around that 180 value, or 1.8 times 10 to the second. Okay, the next stage here is then to change these other values. So you're given values for the motor parameters, and these are what you can see as the different gains throughout the model. And by changing these different values, you'll see that it will have some effect on that output velocity. Let's use something quite intuitive like JM, or the inertia of the wheel or whatever is being spun by that DC motor, because you can imagine as that system has more inertia, it takes more effort in order to get it up to speed. So here the Jm of the system is normally 4 e to the negative 6, and so now we find it here. And so let's do making it just half of that. So making it from the 4, bringing that down to 2. And so then you can click run here. And now what you get is your output speed. What you see is that the output speed is the same, but you see that the transient response is much sharper now. So you can see that within, you can measure the difference in time from 1 to 2, where now it's just 0.05 seconds to move, whereas before, when this was a 4, now I run, and you can see that actually it takes much longer in order to reach that steady state, which is the intuitive response to this, where if you make the system have more inertia, that time response takes longer. And so I invite you to change these different parameters for the motor, for the circuit, for the output load on the end of the motor shaft, and to see what that response would be. The second stage here is to see if we use Simscape instead of Simulink, if we get a similar response. And now the difference between Simscape and Simulink, you have this whole transfer function that you need to create yourself with many different gains and integrations and summing blocks. Whereas Simscape, you can see that most of these aspects have been programmed into more functional blocks with multiple parameters in them. And so let's go ahead and open up Simscape. So here you have the model for Simscape. So now what we're going to do is we're going to add in that voltage sensor here. So from here, the voltage sensor. So double click, voltage sensor pops right up. And now it's important to make sure to rotate this in order to connect the right signals together. So for instance, you have this V. This V is the signal out. You can see it's not actually connected to the input or output of that voltage. And so you can assume that's going to be what's going to your scope. So it would be going through here. So we can rotate this block a couple times. Format, rotate clockwise, format, rotate clockwise, format, rotate clockwise. And so you can bring this signal here. So you just click the signal and drag it. You can see this is the output and this is the input to that sensor. The next being this rotational electromechanical converter. electromechanical converter. You bring this in, matches perfectly, and then the ideal rotational motion sensor can come right in here. And then you can double check how things should be wired. So here you can see that A is actually the what's supposed to be the output signal that goes to your scope. And so this is the signal that has to come here. And then you can refer back to your diagram to figure out where this value C goes. And so C comes back to the mechanical rotational reference. There. Now that you've got this whole system set up, you can do the same aspects that you did with the Simulink transfer function. And so you can see now the model is much simpler than it was in the Simulink case, where this way you have a lot more pre-built functions, like something for inertia. For instance, inside inertia, you can just edit those values directly. So now let's start by running this system to ensure that it's set up properly. And then you can double click the scope to see that output. And so here, same as before, you see that motor voltage input. Then you can see the output position and the output rotational speed. I think in the last graphs, we had the voltage input and the rotational speed were flipped in with their order on the screen. But as before, you can see that you still have these traces that you can use for measurement. Great. The next thing you can do here is we're going to compare between the Simulink model and the Simscape model. So if we go to our Simscape model and we put in the same parameters as we did for the Simulink model. So remember when we had a voltage of 2 here, we had output speed of 45 in the Simulink model. Let me just double check that all of these are the same parameters as in the Simulink model. So we have the resistance of 8. If we go back to the Simulink model, we see that this resistance was also 8. And you can see it's 8 here. And so now we can run the system and we can see if we get a similar output. So here you had this voltage input of 2 volts. And you see that the output is actually half of what it was in the Simulink model. So this means that there's actually probably some parameters that are different between the two models, as both models should give about the same response. And so this one says 20 and not 45. And so now let's investigate which of these blocks is different between the two systems. So if we go to the Simulink, we have 8, 1.2, and 4 times 10 to the negative 6 for the resistance, inductance, and moment of inertia. And so we checked before, we have the 8 here. We have the inductance of 1.2 e to the 3, 1.2 here. And then the moment of inertia of 4, moment of inertia of 4. Then we have the motor speed constant of 0.04 here. So you can see that here, 0.04 is the torque constant, and so now we have to find that torque constant here. And so actually that is the value that needed to be changed. So now this model should be the same as this model. We can double check with this viscous friction of 0.002. 0.002. And this is actually 0.04. Because here, this is 0.04, this should be 0.04. And now, when we click run, we'll get that same rotational speed as before of 45. Now there's one thing to note, and that is that in the Simscape model, this time starts at 0, whereas if we remember back to the Simulink model, this starts actually at 1 here. And the reason for that shift of 1 second is that in the step, we say that the step happens at 1 second in, instead of in the Simscape model, it just happens directly right away. And so with that, you can now try out different parameters in the Simscape model and in the Simulink model to compare the two, just knowing that they should be about approximately the same values as you go through. So here you can see again the scope for Simulink, and you can see that that's about 180 is the speed, and this is when the voltage is at 8. And then if we come to here and we change that voltage to 8, we should get about the same response. And so here you can drag the cursor to see what that actual value is, and you can see again it's 181 radians per second. Okay, thank you for joining this Matlab Simulink and Simscape training session. I hope you learned lots and are interested in using this for your control systems projects. Thank you.